This week we will be looking at rock deformation and structure. So you may have seen something like this as you were outside driving down the road. You'll notice these rock layers, these are sedimentary rock layers, and they are tilted to the right hand side of the photo. Sedimentary rock layers, when they're deposited, are deposited flat lying and horizontal. So when they're tilted, geologists have a clue that something is up. In this case, in the distance, you can see a ridge, and it actually comes up fairly close. This path walks along the edge of the ridge, and in this case, the rock layers are almost vertical. This is a picture I took out in Virginia, and you can see here the rock layers are folded really over on top of themselves. On the right-hand side, you can see a very tight fold. That actually goes underneath and then comes back up and kind of winds around on the left-hand side. So you can see these rock layers are have some very interesting folding going on. So for the geologist, the first thing we want to do is we want to be able to describe the orientation of the rock layers. So since they are originally deposited flat, lying, and horizontal, what we do is we compare them to that original flat horizontal surface. And in geometry, when two planes intersect, you get a line. And in this case, that line is what we call the strike line. You can see the horizontal surface or horizontal plane is in blue, and the rock layers are tilted in the drawing. And where the blue horizontal plane intersects the tilted rock layer, they've drawn a line and they labeled it strike. So that's what the strike line is. And what we then do is we set a compass along the edge of the strike line, and we measure how many degrees east or west of north that strike line points. We can then record that line on a map by drawing the line using the angle that we've measured, or the azimuth we've measured in degrees east or west of north. So that's how we record that on a map. And we're going to do a little bit of that in the lab exercise. So you'll get a chance to see exactly how that works when you do the lab. Now the dip is the angle at which that rock layer is dipping into the ground. And so once we have that horizontal plane defined, we can then measure how steeply or by how many degrees that rock layer is dipping into the ground. And we always measure dip perpendicular to strike, so straight down into the ground. And when we draw it on a map, what we do is we've got that strike line already, and we draw the little dip line perpendicular to the strike line and pointing in the direction that the rock dips. The other thing we do, and you'll see this in the lab exercise, is we then put the number representing the degrees of dip right next to the strike and dip symbol. So for that symbol to be complete in the example they have there, they would write a 50 right next to the little dip line. And that's how we record the orientation of a rock layer. Now, just having one of those strike and dips recorded is important, but what becomes especially useful to a geologist is if we've gone into an area and mapped a lot of rocks and recorded their strike and dips, then we can put all of those measurements we took onto a map with this little symbol, and we can look for patterns. And that, again, is something that we'll take a look at more closely in the lab exercise. So the next thing we want to do is we want to discuss exactly what is going on. So if we see these rocks that are dipping like that, or even more interestingly, folded like this, we wonder what the heck is going on. And so what's happening to the rocks is they're being put under stress. And we have a number of ways to describe the stress that's occurring. And the stress is just the set of conditions that the rocks find themselves under. So most importantly, and what we'll spend the most time talking about, is the type of stress. And so the type of stress, you can see it's got its own list here on the slide. There are two general types, and then the three words in yellow are the really important ones, the differential stress. So the type of stress, the one at the top is confining stress. That's basically stress that's kind of pushing in on a rock from all directions and kind of holding it together. So when you see that rock that's intensely folded, there was probably a lot of confining stress present to allow that to occur. But then if we want to know actually why the rock has taken on the shape that it has, we have to look at the differential stress. And the differential stress refers to stress that is greater in one direction than in other directions. And in that case, we can have compression, which is pushing together, extension, which is pulling apart, and shear, which is kind of a tearing motion. And we'll see this expressed in some of the rocks and structures that we look at in later slides. Some other stress conditions that we're interested in are going to be the temperature. So if a rock is really hot, it's easier to change its shape. Time and rate. If we take a lot of time and proceed slowly, we're going to get one set of responses. If things happen very quickly, the rock will behave in a very different way. And the last thing on this list is the presence of water. That can affect how a rock behaves when it's put under stress as well. So temperature, time and rate, and water are all other stress conditions that are very important when determining exactly how a rock responds. So when a rock responds, we refer to that response as a strain response. So stress is what happens to a rock, and strain is how a rock responds to stress. And we have three types of strain. The first type we don't show, it's elastic. And the reason we don't show it in a picture is because elastic strain is when a rock changes its shape, but then when the stress is removed, it returns to its original shape. So there's really no visible record of elastic strain. However, we can feel what happens when the rock returns to its original shape. Think of an elastic band that kind of snaps back to its original shape when you stop pulling on it or when you let go. And that's an elastic response. When the rocks do this, we feel an earthquake. A ductile response means that the rock retains that new shape. And so in the photo in the upper right, you can see the result of a ductile response. There's some very intense folding in that rock. And last but not least is the brittle response, which is when the rock actually breaks. And so you can see the fractures in that rock that have occurred, those long cracks, and that is the result of brittle strain. So let's see some of the names that we give to these things. So first of all, we'll talk about ductile strain. Ductile strain we usually see in the form of features that happen under compression. So when you compress the rock or when you push on it from the two sides, that's our differential stress. If there's high pressure along with high temperature and maybe a long period of time, it turns out you can actually fold the rocks. And when the rocks are folded, we have two names for the folds. We have a syncline, which is a U-shaped fold. That's on the left-hand side. And we have an anticline, which is an A-shaped fold, which is on the right-hand side. So the arching fold is an anticline, and then that U-shaped fold is a syncline. And that's pretty much it for folds. We'll look at a few pictures. You can see folds come in large, sizes, as in these pictures, but they can also occur in very small sizes in some rocks as well. So this is a picture that I took up near Devil's Lake by Baraboo, Wisconsin. This is a little bit bigger fold. And in this case, you can see the effects of compression. Things were pushing in from the sides. That's what folded these rocks. Now, initially, you might look at these rocks and think they look kind of like clay or shale. So it makes sense that that could deform fairly easily if it's made out of clay. But it turns out when you look at them a little bit more closely, what you find is these rocks are actually a low-grade metamorphic rock. So they used to be clay, they used to be shale, but the high pressure and temperature conditions actually caused a low grade of metamorphism. And when you check out these rocks in the sample, in the outcrop, they're actually slate. Now, the interesting thing about this to me was that the slate, you can see the bedding from the original sedimentary rock has that arch shape in it. But if you look at the layering in the slate, you'll notice on this picture it is vertical. And that layering is our foliation. And one of the rules of foliation is that foliation is perpendicular to the direction of greatest stress. So that was kind of an interesting feature on that. Now, what happens if the rocks break, the brittle strain? Well, we have two types of brittle strain. One would be what we call joints. And joints occur when the rock cracks, but there's no movement. All types of stress will cause jointing to occur in the rock. There are some other causes as well. But if we don't see movement on either side of the fracture, we call it a joint. If one side has moved with respect to the other, we call it a fault. And we have three types of fault that correspond with the three types of differential stress. So the second drawing from the top shows compression. The arrows are pointing toward each other. And you'll notice that one side of the fault has moved up and over the other side of the fault. And that is what we call a reverse fault. If we have extension, which is the third drawing down, you can see the arrows moving away from each other. You'll notice that one side of the fault slides down and away, and that is what we call a normal fault. So that is the result of extensional stress. And then shear stress creates what we call a strike-slip fault. And this view has to be from the top down, and you can see one side is sliding past the other. So we see shear action there, and that's shear stress. Now, if you look at each of those faults, you'll notice that if you put your nose right on the fault, at each of those faults, you would see some shear stress. So when we name the faults, we have to stand back and say what's going on, what's the big picture here, and that's how we get normal, reverse, and strike slip. So let's take a look at pictures of a fault. So this is a picture, this is actually near where I took the picture of the fold with the man standing next to it. Now you may not be able to see the fault, but there is a kind of a yellowish colored stripe running kind of diagonally across this gray outcrop. If we look a little bit more closely, we're going to see it right there. You can see there's a pencil sitting on top of the fault there. So that is our fault. And if we overlay it with some arrows, or I'm sorry, if we look a little bit more closely, you can see the pencil now and the fault is pretty clearly there. And if we throw some arrows on top of it, this is what it looks like. You can see this is the result again of compression. The right-hand side is moving up and over, and so this is a reverse fault. In this case, you have to look pretty closely to see what the movement is. And if you can't see it, that's fine. That's why I drew the arrows and put the labels on the fault. One more fault to look at in the last 20 seconds. This is the San Andreas fault. That's my son standing there. The motion in, 1906 offset this fence by 12 feet. Behind my sun moved to the right. In front of my sun moved to the left.